Hey guys, this is the first exercise video tutorial. These are going to be a series of exercises related to the prior learning objective video. For this video, we're going to cover loops with point arrays, a light introduction into libraries using Rhino script syntax and Rhino common library, getting into programming actual Rhino objects inside of Python. Then we will also cover recursion with a recursive aggregation script, expanding on the introduction to the Rhino common and Rhino script libraries. So we're going to just go ahead and get started. You can find the example files for these exercises, which should match the in-class exercises either on the GitHub or the Penbox. So you can either open up the reference file, or you can just start from scratch, opening up the Grasshopper window like in the last tutorial and making a new GhPyton component. And we're going to just open that up and get started. So I have some stuff from the reference file in here. I'm going to just add these 3 quotation marks at the top and bottom of this coding segment, so that way we can just comment it out so Python knows not to read that. And I'm gonna just go ahead and start from scratch. So when I hit test, nothing is running and we have a clear file. This first segment is going to get into loops and how we can instantiate geometry using loops. The first and most important thing in this is going to be an introduction into libraries. So this is going to be the primary interface from Grasshopper or Python to the Rhino interface. In order to bring in a library or tell Python that we are referencing a particular library, which has a host of pre-built functions, we need to tell it to import. And then we need to give it the name of the library that we're importing. So the first one we're going to import is Rhino script syntax. And then we can give it a kind of nickname. So this makes it easier to refer to later on in the script. So in this case, I'm going to say as RS. So import Rhino script syntax as RS. The next one that I know we're going to need to use is one that deals more with the actual interface of Rhino and less of the geometric objects. So that will be script context. So we can type import space script context as SC. And then the last one is import Rhino, which is the Rhino common library. So once we've done this, since we're operating in a Python script editor inside of Grasshopper, we're going to just need to change the script context document from Grasshopper to our Rhino document. So this is just because Grasshopper is essentially operating in a kind of virtual document outside of Rhino. We just want to make sure that we're declaring that that document is actually the Rhino document. So when we make objects, they don't just appear inside of Grasshopper, they actually appear inside of our Rhino canvas. So we can do this by saying sc or script context .doc equals Rhino doc active doc. So we're setting the sc doc to the current active Rhino document. Now that that's set, we can start by making geometry using the Rhino script library. So we can do this very similarly to how we might do it inside of Rhino, but just using these code references. So first, I'm going to make a variable point pt, and I'm going to say that point equals rs dot add point, and then open parentheses. This is going to call the function add point. So at the bottom here, it's going to actually give us some helpful information telling us what parameters this function takes. So the input parameters are going to be a point3d or a list containing the x, y, and z coordinate values for this point. It is going to then return a GUID, which is, it tells us it's the identifier for the object that was added to the doc. So it's going to be added to this sc.doc, which is the Rhino active doc. So we can now type, we don't have a point3d currently, so we're going to need to type the 3 coordinates. First, I'm going to type 0, 0, 0, following this syntax of the parameters as listed in the help doc at the bottom. So now if we hit test, we can see inside of our Rhino document, 1 point has been added, and it is added at the origin, so 0, 0, 0. If we change each of these values to 1, then we should get a point at 1, 1, 1, which we do. If we make 1 point at the origin and 1 point at 1, 1, 1, we now have 2 points which we can use to establish a line. So first we can visualize those 2 points, and then make a new variable line which stores rs.addLine. And we can see that the input parameters here are a start and end points, so the GUID of those 2 points, so point 0 and point 1, and test. So we now have 2 points with a line connecting them. If we want to make a polyline, we just need a list of multiple points. So to show this, I'm going to add a few more points here. And then we can even, to make it a bit easier, make a blank list. And we are going to add to this blank list. Sorry, actually, we don't even need to do this. We can just specify it after the points and just add point 0, point 1, point 2, point 3. So we now have a list of our 4 points stored in the list points. And then in polyline, we're going to set that variable equal to polyline. And we can see in the parameters, it takes a list of GUID points. So in this case, we're going to feed it list points, close that, and hit test. So we now have a polyline based on those 4 points. If we shuffle the order of those points, so I'll leave this one for visualization, but let's just change this to 3 and then 2 and then hit test. We now have a polyline moving from point 0 to point 1 to point 3 to point 2. We can add a curve, which is a similar input as the polyline, but it also takes a degree input. So we can just feed it the points, and then we can start with 1, and this should give us the same output as that polyline. And now we can change this to 2, and we get a degree 2 curve based on that polyline. Now we change it to degree 3. And we can keep increasing this value as long as it stays below the number of control points minus 1. So for now, this is all of the geometry I'm going to introduce. We can get into the surfaces, B-reps, and mesh references later, but right now I just want to focus mainly on points and some coding structures related to those. So I'm going to comment all of that out. And now what we're going to want to do is, as an exercise, instantiate not just 1 point at a time, but actually use a loop to instantiate a line of points moving along in the X direction. So we can start, if we want to store a list so that we have it in this component. You can see that the reference component has an output variable points. If we make an empty list, we can later append to this so that we have it accessible inside of Grasshopper, as well as actually place into our Rhino scene. Instead of making that 1 point with 3 numbers, which just makes that 1 point based on those 3 coordinates, we can use loops. So for X in range, and then we just need some value here, so let's say 10, and we can now make a point equals rs.addPoint, And let's set this equal to x, x, x. And now let's hit test. So this is now making a diagonal line from 0, 0, 0 to 9, 9, 9. If we wanted a straight line across the x, we're going to want to set the y and z values to 0 and only change the x value in the coordinates for the points. Now if we hit test, we can see a line of points moving across the x axis. We can do this for any of these, hit a line in any axis. But if we wanted to not just make a line, but actually a line of lines or rows and columns, we would need something beyond just one singular loop. So one way to do this is to use nested loops. So if we hit enter, we don't want to just use for x in range, but we also want to do for y in range. And if we tab in this point creation, then instead of 0, 0, 0, we can use x, y, 0, and now hit test. So this is now drawing out points iterating through the x and y values within range 10. So we can see here it's actually starting at the first point in the x axis, and then it's doing the entire row of the y, and then it moves to the next point in the x and then completes that entire row, and so on. This is because for each item in x, so for item 0 in x, we are looping through all of the values in y. So if we wanted to flip this order and actually do all of the items in x first for the y value of 0, and then all of the items in x for the y value of 1, all we would need to do is for y in range 10 and x in range 10. So now it's going to flip the matrix of our array. Now though, I'm going to just keep it as for x in range 10, for y in range 10, and then we can add our last coordinate axis, which is z. So for z in 10, tab in our points so that it's inside of all three of those loops. And now we're going to hit test. Now that we've visualized that and seen how it's actually creating these, we may not want to visualize that. It's slow. It's actually slowing down the computation because Python is thinking that we want to see each frame of the computation. If we don't want to do that, instead just want to see the output of all of these, we can use rs.enable redraw and set this to false, so it will disable the redrawing of the Rhino window until after all of this is done, and then we can call enable redraw true. This is going to disable the redrawing in the Rhino window, run all of the computation, and then draw it all at once. So if we hit test, it now draws much faster and all at once. If we wanted to only redraw, let's say after each row of the y's are done, then we can actually hit enter, tab this out so it redraws less frequently. So it's now doing each entire sheet in the, I guess, y, z, and then progressing to the next unit in the x. So we now have it drawing looping through the X, Y, and Z to create points, and that gives us a 3D array of points. If we want to structure that as a list inside of this points list, there are a couple ways we can do that. We can just at the end here say points.append, then point. This is going to append each point to the list of points, and then we can just at the end here print points and test. So we can see in this output that they're all saved as GUIDs, and it is a flat list of GUIDs. But since we have a nested loop, we have the ability to actually store the values in columns and rows. So we can do this by making additional variables inside of each of these loops. So one can be row, and the other can be column. Now, for every iteration here, we're going to append to the column list our point, and then tab out, and after it has gone through all of them, all of the columns in the Z, we can append to the row, and then at the very end, append the row to the points and print our points. Now if we hit test, we can see that it's no longer a singular flattened list. Instead, it's a nested list or a three-dimensional array containing rows and columns and then two-dimensional sheets. So we now have this creating 3D points in an array. This is always making, though, a set of 10 points. So if we wanted to change that value, we would just need to edit the value inside of the range function. So one way to do that is to set a variable here. So var equals 20, and then we can copy var and paste it where we have 10. And this is now going to make 20 points from 0 to 20 units in the X, Y, and Z directions, which we can see has doubled that in each direction. If instead of setting this variable inside of the Python script, we actually wanted to set it inside of Grasshopper, we could just right-click on one of these inputs, type var, and then hit test. Right now it's going to say range integer and argument expected got none type. That's because we have no input going into our R input parameter. So what we need to do is double left click in the Grasshopper canvas and type a number, which will give you a number slider. So I just typed 3. I can plug this into var, and if we hit test, right now it's giving us an error saying that range integer and argument expected, but instead it got a float. This is because anytime these Python script components read a number, they're going to default to certain types of variables. So to fix this, we can right click on that variable, go to type hint, and we're going to tell the Python script which type of variable this is. So this is an integer. So we can click on int, and we now see it running the 3D array with 3 points in each direction. Now, as we edit this slider by double clicking on it, we can change the value. So let's try 7. And now there are 7 points in each axis. If we wanted to not only make the points, but actually give them a color value, one way that we can do this is by after this add point, we can create a color. So color, type color equals rs dot color, open parentheses. This is going to tell us that the function create color takes a 3-number input to create the color. These are going to be RGB values and are going to be from 0 to 255. So what we can do is say, take our whole range, so that's the var value, and our current x, y, and z, so x, and then we're going to divide that by our full range var and multiply it by 255 so that we get the full color range. We can do that in each of these by dividing the y by var and then multiplying it by 255, and the z by var, multiplying it by 255. Now we've just created the color, but we haven't actually applied it to anything. So next we actually need to type rs.objectColor. And here we see that the parameters it takes are an object or list of objects and a color. So we're going to feed it point and then the color for that point. And we don't need to change what we're appending to this column list because it is going to actually update the point itself and not the reference to that point stored in that variable. If we want to make more of these points, we can just, and our slider doesn't go up high enough, we can right click, go to value, change the maximum value. So let's try 100. And then I'm going to double click and type 80. And we may have to wait for a second, but it will make an 80 by 80 by 80 3D array of color points. Our window is moving a bit slow inside of Rhino, so be careful going much higher than this resolution. But we have our 3D cube of points. There are many other ways of kind of iterating through a similar exercise, so please try this on your own and try and figure out the coolest variation of this. You can vary the x, y, and z coordinate values relative to these loops. So you could do x divided by 2 and then keep y and z the same. So I can show that on a smaller value array. I think this just did. There you go. So it's half the value now in the x as the y and z. Or you could do a similar thing by saying only 100 for the x, and it's going to adjust the color values. So now they favor the green and blue spectrum more. But try to be creative with what you can kind of produce with this. Maybe even try to make something besides just a cube. Maybe use mathematical functions to vary the placement of these x, y, and z points, and make something that kind of breaks this intro to Python exercise, especially if you've already familiarized yourself with Python or Grasshopper.